Hello everyone, I'm going to present our work on estimating object dynamics in hand using tactile fingertips. We are affiliated to the School of Computing at University of Utah and NVIDIA. Real-world robot manipulation can greatly benefit from knowing an object's dynamics. For example, consider the task of grasping, where knowing the friction coefficient could aid in better grasp planning and also in preventing slip after grasping. Knowing an object's physical properties can also enable robots to perform highly dynamic tasks, such as targeted tossing, as shown here. However, in the real world, it's impossible to know the dynamics of every object. Objects can also exhibit different dynamics based on its contents. For example, a filled cup would behave very differently from an empty cup. Hence, estimating object dynamics online is a more realistic setting for enabling robots to work in unstructured environments. Classic approach for dynamics estimation involves mounting the object to the wrist of a robot which has a force torque sensor, and moving the arm rapidly to excite the dynamics of the object. However, this is impractical for autonomous robots as they will require switching out the end effector, and this also cannot handle delicate objects. To enable autonomous robots to infer object dynamics, we explore a more realistic setting. Our setup consists of a robot with a dexterous hand, equipped with tactile fingertips that can observe contact forces, and a camera to track the object in hand using depth. In this realistic setting, we have some limitations in what we can observe. First thing is that we cannot sense torques from the fingertips. We can only observe linear forces. The sensed forces not only contain the force due to the object dynamics, but also the force applied by the other fingertips on the object. Additionally, object pose measurements from a vision-based tracker tend to be noisy due to occlusion of the object by the robotic hand. We will now look at how these limitations affect our sensor measurements. We first collect data by grasping the object and moving at high speeds, as shown here. We track the object pose by using DART, which is a depth-based tracker. There are many instances where the object pose tracking fails due to occlusion and noisy depth readings. Here, the object flips in the tracker, while in the real world it remains in the same orientation. Now let's look at how the forces look. On the left, you see forces that are sensed by a wrist force torque sensor while the object is rigidly attached. And on the right, we have the net force on the object from our setup. Our setup has a much more limited resolution as the tactile fingertips observe forces applied by the other fingertips in addition to the force due to object dynamics. With these limitations in sense observations, we explored two separate approaches to estimate object dynamics. We first estimate friction by force servoing while the object is still on a table, and then estimate inertial parameters by formulating the in-hand object dynamics as a factor graph optimization problem. Given a grasp on the object, we hold the object in hand using the fingertips. On the right, we show an illustration of the surface normal with respect to the object surface around the index fingertip. To estimate friction, we serve a force applied by the index fingertip on the object surface. We start with the force being parallel to the surface normal, shown here by the red vector. We then servo the force away from the surface normal until slip is detected at the fingertip. We then use the angle between the force and the surface normal right before slip to compute the friction coefficient. We validate this approach on 10 different surfaces from 8 objects. We run the experiment 10 times per surface. We compute ground truth by using the slope test and show them in the plot as red crosses. We see that our median estimates are very close to the ground truth estimates across all objects. We'll now describe our approach to estimating the inertial parameters, specifically the mass, center of mass, and the inertial matrix. Here is our factor graph, where the states are indicated by Circles and factors between them are represented by shaded boxes. Our state consists of the object pose, contact point of the fingertips, and the forces at these contact points. We also represent the inertial parameters as part of the state. Object pose estimates from Dart are encoded via the measurement factors into the object pose state. Force and contact point measurements from the YTAG are encoded in these measurement factors. We use multi-sample dropout to obtain uncertainty estimates of the force predictions. This uncertainty is also input to the measurement factor. We set up the Newton-Euler dynamics equations as a dynamics factor between three consecutive time steps of object pose observations: the current contact point and the force from the fingertips. We use finite difference in SE3 to compute the acceleration of the object from pose measurements. To ensure physical consistency, we enforce constraints on the inertial parameters. Specifically, the mass needs to be positive, the center of mass needs to be inside the convex hull of the object geometry. We also enforce physical consistency of the inertial matrix by representing it with a rotation matrix and a diagonal matrix along the principal axis with non-negative elements. This is similar to Professor et al.'s work from 2016. We can also encode any prior on the inertial parameters by using the inertial distance, which was also used by Lee and Park. To avoid biasing the results with a good initial prior, we will only discuss results that does not use this prior in this presentation. Now let's validate our inertial estimation. We validate this approach on three different setups. We first validate on the classical setup of attaching the object to the wrist. We also simulate a box that has force applied at 4 different contact points. Here we study results of varying degrees of noise in these sensor measurements. We finally validate on our realistic manipulation setup, which uses forces from tactile fingertips and noisy pose estimates of the object from a vision-based tracker. We compare our method to a factor graph implementation of the standard least squares approach. This baseline also incorporates measurement factors but does not use the physical consistency factor or the prior factor that is in our approach. We see that the baseline performs reasonably well in estimating mass across all three setups. Our approach only performs better or similar with the classical setup and simulation. With the realistic tactile fingertips, we perform worse, and we suspect this to be because of the insufficient excitation of the object's dynamics. To compute the error in the center of mass and the inertial matrix estimation, we use the inertial geodesic distance as the error metric, as it gives us a normalized scalar distance between two sets of inertial parameters. The baseline, which is shown here, performs well on wrist-mounted setup as shown by the small inertial distance between the predicted and the estimated inertial parameters. However, it performs worse in simulation and becomes unusable in our tactile fingertip setting. A proposed dynamics factor graph based approach, on the other hand, performs significantly better in all these three cases, even without the use of the inertial prior. Now let's see how these estimates can help us. So here is a physics simulation comparing how an object would move when a constant force is applied. We compare our inertial estimate to the baseline estimate. The green box contains the ground truth object dynamics, and the red is the same object, but it uses the estimated dynamics. Now let's play this video. We can just from visual observation see that our estimate tracks the orientation better than the baseline. We can also see this numerically, where though the position error is worse in our estimate, the orientation error is 10 times larger on the baseline compared to our approach. Thank you for listening. Visit our website for more information.